2, 1. Okay, this is the third and final part of this video series on the definite integral. So we talked about the theory behind what the definite integral is in terms of the area under the curve, and we looked at some properties of the definite integral. Before we talk about how to evaluate the definite integral, I need to make a point here. And that is, just because a function has an antiderivative does not mean that the definite integral on a particular set of boundaries actually exists. In order for the definite integral to exist, your function has to be continuous on the interval from a to b. And if the function is continuous on the interval from a to b, we say it is integrable. That is, the definite integral exists on that interval. So what allows us to evaluate a definite integral, actually find the area under the curve, is referred to as the Fundamental Theorem of Calculus. And what it says is that if f is a function that is continuous on an interval from a to b, then we evaluate the definite integral of that function by taking the antiderivative of the function, and then we evaluate the antiderivative at the upper bound, we evaluate the antiderivative at the lower bound, and then we subtract the two, upper bound minus lower bound. Alright, so we use our standard definition that capital F is the indefinite integral, or the antiderivative of f. Alright, then we can evaluate this definite integral right here by taking capital F of b and subtracting capital F of a, and we have the area under the curve bounded between a and b. Alright, now there's some notation that goes along with this, and the notation I want to look at is right here. Alright, we have the notation for the integral, alright, for the definite integral. And what we do is we take the antiderivative, and you use this little vertical bar here with the bounds to say that we're going to evaluate it at a to b. Alright, so let's say right down here at the bottom, I've got the definite integral of x dx from 1 to 3. So I take the antiderivative of x, which is x squared over 2, or 1/2 x squared, the way I've been showing it in class. And then this just denotes that I'm going to evaluate it from 1 to 3. Alright, now before I actually show you the bottom part of that and what we get, we need to talk about constants, because you know when you take the antiderivative you get a constant. So let's look at a simpler example here. First of all, let's look at why it might be that that's what we want to do, that we want to take the difference in those areas. Take a look at this simple function here. Alright, this is just a line y equals x, or f of x equals x, okay, which is what I had in the last example. When I sketch this out from 1 to 3, notice what I get. It's actually just a little trapezoid, and a trapezoid we have a geometric formula for. If I look at this in terms of the geometry, I can look at the two squares that get made by the bounds, right? I have a 3 by 3 square here, and I have a 1 by 1 square here. Right? So if I were to take the area of this 3 by 3 square and then subtract out the area of the 1 by 1 square, I would have this L shape here filled in. If I then bound that by the curve, then I have just the lower trapezoid here. Alright, so you can have that picture in your head as to why we have to subtract the function values at the end. Alright, but let's see what happens with the constants, right? Because anytime you take an antiderivative, you end up with a plus c. Right? So I take the antiderivative of x, and I get x squared over 2 plus c, and then I bound that from 1 to 3. And I evaluate. Alright, so I do f of 3, so I plug 3 in, and I get 9 over 2 plus c. And I plug 1 in, and I get 1 over 2 plus c. But I'm subtracting the 2, so when I subtract the 2, what happens is the c's essentially add up to 0. Alright, now that's always going to happen. So because that's always going to happen, when we're evaluating the definite integral, you basically ignore the constants. Okay, so you don't need to worry about the constants when you do the definite integral. So like if I come back over, whoops, where was I? Here. All right. The way you would write that out is just like this. Okay. All right, you take the antiderivative, x squared over 2, evaluate it from 1 to 3, plug in the 3, plug in the 1, add everything up, and you get the area under that curve. Okay? That's going to be it for right now. When we get back to class, I will run through this again, along with any questions you might have. This actually covers a good deal of definitely 6.3, which I asked you to read already, but 6.4 also, and a little bit of 6.5. All right, so if you have the urge to read ahead, feel free, and I will see you all in class.